Classically, if I put a particle in a 1D box of length L, I'm equally likely to find it at any particular position x within the box. In other words, the probability density classically is a constant. Normalizing, we would find that this constant is 1 over L. Then the probability that the particle is found between, say, position x1 and x2, we could calculate is just equal to the integral of that probability density from x1 to x2, which is just proportional to the distance between the points. Quantum mechanically, the story is a little different. For a particle described by a wave function psi, the probability density is given by the absolute value squared of psi of x. Consider the following problem. Find the maximum and minimum probability density for the nth state of a particle in a one-dimensional box. What is the probability of finding the particle between x equals L over 4 and x equals 3L over 4 for the first 4 energy levels? What about for n equals 101? Let's start by solving for the wave function of a particle in a 1D box. So the potential is infinite at x equals 0 and x equals L, and the wave function is thus 0 for x less than or equal to 0 or greater than or equal to L. Inside the box, the potential is 0, and so the spatial part of the wave function satisfies the time-independent Schrodinger equation, minus h bar squared over 2m d squared psi dx squared equals e psi, where the full time-dependent wave function is given by the spatial part plus times e to the minus I omega t. So the most general solution to this equation is psi of x equals a sine kx plus b cosine kx, where k is the combination of variables here, root 2me over h bar squared. It's the wave number of the particle, and so it's also related to the de Broglie wavelength of the particle, k equals 2 pi over lambda. And of course, this only holds for x between 0 and L. Next, we need to apply continuity of the wave function at x equals 0 and x equals L. So continuity at x equals 0 says psi of 0 equals 0, which implies that b equals 0. So the cosine term goes away. Continuity at x equals L says psi of L equals 0, since the wave function is 0 outside of the box. And what this one says is that sine kx, sine kl equals 0. So the argument of the sine has to be an integer multiple of pi. So we'll write that kl equals n pi for n a positive integer. 1, 2, ... Importantly, n can't be 0, n is greater than 0. And this is because n equals 0 would give a trivial wave function, so no description would be possible for n equals 0. A thing to note about this formula is that what it told us, what continuity told us, given what we wrote up here, is lambda over 2 equals, let's see, L over n. In other words, an integral number of half wavelengths have to fit in the box. Okay, so let's write what we have so far. So far we've solved for the wave function psi n of x equals a sine n pi x over L in the box. Where the subscript n is important, what we found is that there's a specific wave function, psi n of x, for quantum number n, for the state with energy En, or as we wrote here, wave number k equals n pi over L. So next we need to normalize the wave function so that the total probability of finding the particle somewhere in the box is 1. So we write this, 1 equals integral minus infinity to infinity absolute value squared psi n x. And so try doing this at home, and the details are in the attached PDF to this video. But what this will tell us is it'll give us a equals root 2 over L. Okay, good. So let's write our answer for the probability density. We found that psi n of x for the state with wave number n pi over L equals 2 over L sine squared n pi x over L for the particle in the box. So the argument, so sine squared here runs between 0 and 1. So this probability density is a minimum when sine squared equals 0, or when the argument of the sine is an integer multiple of pi. And that'll happen when x equals L over n times some integer. Let's call it m. Where m runs up until n, since at m equals n, x equals L, and the wave function is only non-zero inside the box. Then this probability density will be a maximum when sine squared equals 1, which happens when its argument is equal to a half integer multiple of pi, which we can write as L over n, let's call it m prime plus 1/2, where again, m prime is just some integer. Here it'll go up to n minus 1 for the same reason that this one only went up to n. And of course, n is a positive integer, 1, 2, etc. So we've answered the first part of our question. These are the maxima and minima for the probability density for a particle in a box with for the state with quantum number n. Let's plot what this probability density is for the first few n. I've plotted the probability densities for the first 4 states. Remember, classically we said this would be a constant, which are these blue lines that I've drawn on the plots. Quantum mechanically, something I want to point out is that there are actually places where there is 0 probability of the particle being seen. These are the minima we just computed. Now, you might ask, how can that be? If the particle can be found on either side of those minima, how can there be places where the particle has 0 chance of being seen? And of course, the answer is that the particle does not travel from one side of the box to another on a classical trajectory. It is not a classical solid object. It only exists at a particular place when it is observed to be there. And these plots tell us about the probability that we will observe the particle at particular positions. Now, this plot down here is for the n equal 101st state. You can see that the distances between maxima and minima are becoming much smaller, and the distribution looks much more uniform and continuous. This is actually what we'd expect. In fact, from our formulas we wrote earlier, we have that lambda over L equals 2 over n. So as n gets large, as the quantum number gets large, the wavelength of the particle becomes small compared to the length of the box, which means we'd expect to reproduce classical behavior, which is what we're seeing in this plot for large n down here. So next we can compute the probability that the particle will be found in the center region of the box from L over 4 to 3L over 4. Now remember, classically, we said from our discussion in the introduction, this probability would be 1/2. The particle would have a 50% chance of being found in 50% of the available space. Quantum mechanically, we can figure this out by doing this integral over the probability density that we derived earlier. So in the attached PDF to this video, I do this integral for general n. And so I encourage you to try doing this at home and to compare with the PDF. What I'm going to show you now is the answer for the first 4 values of n in the form of a plot. The dotted line here corresponds to the classical prediction. We see that the even n states actually match the classical prediction, while the odd n states don't. The n equals 1 state actually has a much higher probability of being found in the center region of the box, while the n equals 3 state has a lower probability of being found in the center region. Here, we've plotted these probabilities all the way up to n equals 1, the n equals 101st state. We can see that for small n, the probabilities have a very non-classical behavior, but as n gets large, they converge to the classical expectation.